So here's part 2 on section 7-2. We're on question 3, and what we're doing is just going through more examples on converting parametric equations back to rectangular equations. So number 3, just like the others, you kind of look at it and decide, which one's easier to get t by itself. And in this case, I would say that getting t by itself is easier in the x equation. So I'll do that here. I'll just say x is equal. I guess I didn't need to exactly copy the whole thing, but I'm going to divide by -3. So negative x over 3 is just what t is. Then we're just going to substitute. I'm going to bring it down here. So here we just have y is equal to t squared. So that's where x over 3 squared plus 2. When we square this, the negative does go away. So so squaring a negative just makes the negative go away. The x is squared and the 3 is squared. So we get y is equal to x squared over 9 plus 2, and we are done. We're boxed in. We should probably graph this. I'm going to switch over and set up the graph on the calculator, and that way it kind of saves some video time. Let's see. So if we go to our calculator, so in the x and y and parametric, that is our -3t for x and t squared plus 2 for the y. When we hit graph, we get a parabola that is vertex is 0, 2. So we want to sketch this. We would just 0, 2, and then it just kind of goes up from there. Again, when we sketch these, the key features for parabolas, the big one would be the vertex. Anytime you can get, say, an x or y intercept, that's great. This one doesn't have any x-intercepts, so we just kind of sketch to the best of our ability. All right, number 4. I'm going to look at number 4. I would say, well, let's just get y by itself, or t by itself in the y equation. So we'll say y over 4 is t. Now x is y over 4 squared minus 5. So if you follow these steps, though, what you notice is I'm not distributing my squared, the y over 4 squared yet. I could, but I'll eventually take a square root anyway. So at this point, if you follow the process that I'm doing, I have the y over 4, the squared term by itself on one side. Then I can say plus minus square root of x plus 5 is equal to y over 4. Now, that was a lot cleaner than saying y squared over 16 is equal to x plus 5, and then multiplying, and it would have gotten a lot messier. Maybe we can take another video and demonstrate the other way of doing that problem. But for now, I would just say 4. Let's start over. Y is equal to 4 times the plus or minus square root x plus 5. And you could bring the plus or minus out front and say y is equal to plus or minus 4 square root. Either one of those would work. They do mean the same thing. And since it's multiplication, that plus minus can go out front. But again, we want to graph this and check it. I know for a fact what these look like and how, honestly, these don't necessarily, I don't need to graph these ahead of time. I should be doing that, but again, to save some time, I'm just graphing them last to double check my work. If we switch over to the graphing calculator here, I already entered it in, and what we have is the equations, t squared minus 5 and 4t. We get our sideways parabola. Again, y is going to be the what's squared really in the end here. We're looking for our x coordinate. 1, 2, 3, 4. Our x-intercept. 1, 2, 3, 4, 5. We go over to here. Make sure we get our red marker. 5. And we open sideways. So there you have it. We have our graphs, 3 and 4. I'm going to pause just to get set up for the next couple examples for a second here. So I'll just hold on. So switching over, here's examples 5 and 6. Now, example 5, I will say, and we did this in class, this is a good example. Any trig function parametric, I highly encourage putting that into a calculator first. The algebra can get really messy. So let's do this. Let's just plot that right away. In fact, let me get to 3 cosine, so 3 cosine and 3. Okay, I'm going to graph that. Looks like an oval, but if I go zoom 5, maybe zoom 5 is the zoom square. So that just gives us that proportionality and gives us a circle. So now, the thing about these ones, especially these trig ones, if I see that this is a circle, and I see where its center is, and I know what its radius is, I don't need to do the algebra of this problem, per se. I can see that this is a graph of a circle. And I know what the standard form equation for a circle is. So I'm going to just identify the center, 0, 0, and the radius 3. Therefore, my equation in rectangular form is just x squared plus y squared is equal to 3 squared. And we're done. So this is a good example where using the graph is extremely beneficial. And if you want, come see me in class. I will gladly explain what the algebraic side of that would look like. But what you end up doing is finding the sign of the cosine inverse of the fraction x over 3, which is something we haven't talked about this year. You should have seen it last year. It just doesn't come off as easy. So anyways, we're going to do 6 and finish this video out. So in 6, I see that we've got, well, frankly, we've got 2 options. I'll solve for t in the x equation because, and the only reason for that would be, well, first of all, we have 2 t's in the y equation, but also if I solve it in the x and I plug it in for y, I already have that y equals part of my equation done. I don't have to re-solve for y. So anyways, I'm going to solve for t by itself using the x parameter. So x square roots of t equals 1, and then the square root of t equals 1 over x. Now I'm going to square both sides and get t is equal to 1 over x quantity squared, or just 1 over x squared. Then I'm going to bring this down. I'm going to say y is, so 1 over x squared plus 1 all over 1 over x squared. What I can do, legal algebraic terms, or sorry, steps, I can take this fraction, since I have one term on the bottom, I can create two fractions and say 1 over x squared over the denominator. So first term over denominator, and then plus, because it's a plus there, then the second term over denominator. So what we end with is this term, 1 over x squared, over itself is just 1. And here I have 1 over x squared, which is the same as 1 times its reciprocal, x squared over 1. So 1 times x squared over 1, this whole thing just becomes x squared. So the final answer is just y equals 1 plus x squared. And if we look at our graph in here, we'll clear this. One divided by square root of x, and quantity t plus 1 over t. If we graph this, well, let's see. It looks a lot like x squared plus 1, or 1 plus x squared, but we have a problem. We have not quite the same graph. In fact, if I zoom, maybe I'll just change my window to be 0, 0. Gives me a little bit of a zoom. But here's the problem. We're only getting half a parabola. So this kind of brings me to my next point, which was we haven't seen this per se yet. But anytime we do parametrics, let's go back to our instruction. The instructions do say write each pair in rectangular form, graph the indicated direction, but then the last statement, state any direction or any restriction, on the domain and justify why the restriction is needed. So it's saying state the restriction on the domain. So what that means is, and here's a good example, we have a graph that in parametric mode does this. That's the parametric. If I graph this in just traditional y equals mx plus b, that traditional rectangular form, that graph looks like this and goes to both sides. What it is saying to do is we need to include a restriction of our domain. If I graph y equals 1 plus x squared, I don't actually get the same graph as the parametric. What I get is extra graphing, extra blue lines. So if I instead said, hey, that parametric looks like 1 plus x squared, but we need to keep in mind that x has to be greater than 0. And why is that? Well, physically, if you look at the graph was approaching 0 and then stopped. The question is, can it equal 0? Can x equal 0? And the answer is no. I'm actually running out of time on my video here, so I can explain that for those who need it, but typically we look at the graph to determine what our domain restriction of, like in this case, the rectangular blue graph. But that is it for those examples. I've got 2 more, examples 7 and 8, and I will get a 3rd video out here shortly.